Solubility-Product Constant. So the process by which an ionic compound dissolves is also an equilibrium process. So the solubility-product constant, KSP, here the SP is for solubility product, is an equilibrium expression like those that we learned to write for other equilibrium reactions for a chemical reaction in which we have an ionic compound dissolving. So we remember that solids are omitted from the equilibrium expression because their concentrations don't change. A large KSP means the compound is very soluble, and a small KSP means the compound is not very soluble. So we might have something like this. Well, let's just go to this one. Forgot to enter drawing mode again. So what do we do with this? Well, the first thing we have to do is we need the chemical equation, the chemical reaction, showing the solid compound in equilibrium with its dissolved aqueous ions. We're talking about something dissolving, and so we're going to put the solid as the reactant, and it's going to be dissolving into its ions. So here we have barium sulfate. When that dissolves, it forms barium 2+ ions and sulfate 2- ions. And then we write the equilibrium expression for that. Remember, it was the concentrations of the products raised to the exponent of their coefficients, there's no coefficients in this one, divided by the concentration of the reactant, but because this is solid, we leave that out. So the equilibrium constant is going to be the concentration of barium ion times the concentration of sulfate ion. In these KSP expressions, there's not going to be a denominator because the reactant side is always just a solid. And instead of calling it KEQ, we call it KSP because it's something dissolving. So we're not going to get hung up on, did you label it KSP or KEQ? That's a trivial thing. Writing the expression is what's important. So if KSP, which is a number, it's a constant, if that is a large number, that means that the concentrations of these ions are going to be high, right? And if KSP is a very small number, then the concentrations of these ions must be very small, meaning that the solid does not dissolve very much. Does that make sense? Yes. So look at these numbers. Some of these are really small, like lead 2 sulfide. Now, if you remember from our solubility chart, lead sulfide was considered insoluble. And here it's got a solubility product constant of 9 times 10 to the minus 29. Okay? So there are some lead and sulfur ions that do dissolve, but very, very few. The concentration of them is so low that when you multiply them together, you get 10 to the minus 29. Here's another one, copper sulfide. That one's really tiny too. 10 to the minus 36. Calcium carbonate, 10 to the minus 9. That's also considered insoluble. Question?
So what numbers are they multiplying together to get those numbers?
That's a good question. What numbers are they multiplying? Let's look at calcium fluoride. So for calcium fluoride, we would first the equation. So calcium fluoride, a solid, going to be in equilibrium with, I'm going to leave out the state symbols because I don't have room. It would be 1 calcium ion and 2 fluoride ions. And so the expression for that, KSP, is going to equal the calcium ion concentration times the fluoride ion concentration squared because of this 2 here. So the way they come up with these solubility product constants is you put some calcium fluoride in some water and you stir it up and you give it plenty of time to dissolve, and then you measure the calcium ion concentration You measure the calcium ion concentration, the fluoride ion concentration, and you get actual numbers, and then you multiply them according to this equation, and you come up with this KSP of 1.46 times 10 to the minus 10.
So for ours, we just use the table.
We just use the table. Yep. So what we're going to do is we're going to use this table to find out what the concentrations of the ions might be. Yeah, so we'll use it backwards. So this, a table like this is like, oh, great, all those numbers. This represents hours and hours and hours and hours of work. People doing this in different labs at different times and testing and checking and averaging to get these nice numbers for us. So let's write KSP expressions for each of these ionic compounds. So we're going to start with the compound listed as the reactant. So AgI, and that's a solid, and we're going to dissolve it in water. So that's going to be in equilibrium. We're going to take that ionic compound and separate it into its individual ions. So we've got silver. That's going to be aqueous. And we've got iodide. We know the charge on iodide from the periodic table. It's -1. We do need a charge on the silver ion. We're supposed to remember that silver is +1. Aluminum's +3, and you go down the stairs. Aluminum's +3, zinc is +2, silver's +1. If you don't remember that, for this one you could look at the charge on the iodide and see that this is a 1-to-1 ratio. If the iodide's -1, the silver must be +1. Now, you could write the KSP expression and be pretty good with that and still have the charges screwed up. So it's not a big deal, but we're going to try to get things exactly right. So we've got our equation now. And so then we say KSP equals, equilibrium constants are always the products divided by the reactants. So there's the concentration of silver plus and the concentration of I minus. And were there any coefficients in this equation? There were not, because one silver iodide creates one silver ion and one iodide ion. And so there's no exponents in our KSP expression. So that's that one. So let's do this next one. Calcium hydroxide. Put that as a solid. What's the first ion? Calcium 2+. How do we know it's 2+? Yeah, that's one way. The hydroxide's -1 and there's 2 of them. Periodic table tells us as well. Calcium's in group 2, so it's 2+. So we've got calcium 2+, and then what's the other one? Hydroxide. If you didn't remember the charge on the hydroxide, you could figure it out from this formula. How many hydroxide ions? 2. These equations need to be balanced. They're generally pretty simple to balance because you've just got this one thing coming apart. So in here there's 2 hydroxide ions, so over here there's going to be 2 of those. Remember that it's always 2 ions. Okay, sometimes people get a little too creative and they try to put the oxygen and the hydrogen separately and make this big crazy thing. 2 ions, okay?
That's always?
Always, in this class. There are some things that have more than that, but not in this class. We get to, stay with the simpler. So yeah, there's that one qualification. In this class, 2 ions. Almost always the metal ion, which is the first element, and everything else. What's the exception to that? There's one polyatomic cation, ammonium. and H4. So then our KSP for this is going to be what? Brackets, calcium ion, raised to what power? 1. So we don't need to write that. And then what? OH negative in brackets raised to the second power. Any questions? It's just an extension. I mean, we really have done this before. We just didn't call it KSP. We called it KEQ. We don't include the reactant in the denominator because it's a solid. Solids and liquids do not change concentrations. So we can use the KSP value to find the solubility, the molar solubility of a compound. So when we talk about the solubility of a compound, it's the amount of compound that dissolves in a certain amount of liquid. So the molar solubility is the number of moles that will dissolve in 1 liter of solvent. So you put the solid in a liter of water. What is the concentration? How many moles of it dissolve? So how can we determine the molar solubility, which is given the symbol S, of silver chloride? Here's the reaction, the equation for the dissolution of silver chloride, and here's its KSP value. We're going to need the KSP expression. We also need to enter drawing mode. KSP. So this is going to be the concentration of the silver ion times the concentration of the chloride ion. And we know that that is equal to 1.77 times 10 to the minus 10. If all of the silver ion came from silver chloride and all of the chloride ion came from silver chloride, what can we infer about the relationship between the concentration of silver ion and chloride ion? They must be equal, right? Because they came in paired up and we're separating them, but we're going to have equal numbers. So we can say that the concentration of the silver ion is equal to the concentration of the chloride ion because they came in together. It's like you're having, I don't know, a marriage retreat, and you've got 100 married couples show up to this event. What's the relationship between the number of men and women? It's going to be equal, right? Because they came in paired up. So silver ion equals chloride ion. So how about if we call that S? Just like randomly, not thinking about what we're doing or going forward or anything. Just call it S. Well, let's just write over this maybe. Come on, I want a different color. I'll go with purple, see if that works. Let's go with fat purple. Can you do fat purple? Come on, you can do fat purple. Maybe not that fat. Just talking to she likes it when I talk to her. There's S, and then the chloride also equals S. Right? Because the silver ion concentration is equal to the chloride ion concentration, and they each equal S. So I'm just putting S in for them in the equation. So then this number is equal to what? It's equal to S squared. Right? Can we figure out what S is? Yeah, we have to take the square root of both sides. Here we've got S squared. If we take the square root of it, that's undoing that function, then we'll get S. And then we have to take the square root of this guy as well. So you definitely need a calculator for this one. 1.77 EE minus 10 square root. So S equals 1.33 times 10 to the minus 5. Is there a unit on that? Remember, the units with these equilibrium expressions are kind of weird. These concentrations, the bracket tells us the concentration in moles per liter. We used capital M as that abbreviation. And because the products, the solubility constants can end up being all kinds of different things depending on the ratio of ions, we leave them unitless. But when we go back and we find a concentration, then we just understand that the unit is moles per liter. So this is telling us that 1.33 times 10 to the minus 5 moles of AgCl will dissolve in 1 liter. That's not very much stuff. 10 to the minus 5 moles. And we consider silver chloride to be insoluble. But a little bit of it does dissolve. Any questions? So let's do this guy. Calculate the molar solubility of calcium sulfate. Anybody thinking, where's the number? Don't we need a number? We have to go look it up through the magic of PowerPoint. It was calcium sulfate, right? Here's calcium sulfate, CaSO4, 7.10 times 10 to the minus 5. So KSP equals 7.10 times 10 to the minus 5. You do not need to memorize or write down those product constants, okay? I will give those to you. Those are something that you just go and you look up. It's a reference thing. So calculate the molar solubility. What do we need? We need the solubility product constant, or the solubility product expression, right? We need that formula, but to get the formula, we have to do what? Write the equation. Isn't this fun? Fabulous activity for the returning from spring break. So calcium sulfate as a solid dissolving. So that's going to make a calcium ion, Ca2 plus because it's in group 2. And then everything else together, the SO4, 2 minus, that's sulfate, and that will also be aqueous. From the formula we see that there's 1 calcium ion for every 1 sulfate ion, and so in our equation here we've got 1 calcium ion and 1 sulfate ion, and this equation is balanced. KSP then is going to equal the concentration of the calcium ion times the concentration of the sulfate ion. And just like in the previous example, we know that this guy and this guy came in together and they just separated, and so there must be equal in number. Yes?
Now, you know that they're equal because their coefficients are equal.
Yes.
So
We know that they're equal because they each have the same coefficient. Here's a 1 and a 1.
So if it's 1 to 2.
If it's 1 to 2, we can't say that.
Okay.
Yeah.
I was going to say, what's the point of doing the whole equation if we just take the square root?
There are lots of other things that are different. We're not going to go there because that gets it's just beyond the scope of this class. So can you solve for those things? You can. We're not going to do it. You end up with quadratic equations sometimes, and right, yeah. That's the correct response to quadratic equations. Oh, at least he didn't fall out of his chair. We're not doing quadratic equations in here. So we can all be thankful for that. We're just going to do the ones that are one-to-one like this. But this gives us the idea, it's kind of, we're playing in the wading pool. And for those of you that need to go on and take Chem 1, after having practiced in the wading pool, then you can go into the deeper water and do the crazier stuff. Okay. So we know that the calcium ion concentration is going to be equal to the sulfate ion concentration. And again, let's call that S. So then we know that KSP must equal S squared. So we've got S squared is equal to KSP, which we looked up and found to be 7.10 times 10 to the minus 5. So then S must be the square root of that. And this is another place where if you're doing something unconventional with scientific notation on your calculator, you need to be careful. Because when you use that EE or EXP button, that's telling your calculator this is one number. I want the square root of the whole thing. So if you've got one of those funky calculators that has the times 10 to the x button, you may need to use some parentheses here. So just make sure that you can get your calculator to give you the correct answer. And I'm coming up with 8.43 times 10 to the minus 3. And the concentration would be moles per liter, capital M. Any questions?